What's up, AP Stats Cats? We are looking at 6.1b, continuous random variables. Before we were looking at discrete random variables, correct? Discrete means they're countable, like 1, 2, 3, 4. And then we just make a histogram of the probability of those. But not everything in the real world works that way. There's a lot of things that are, like if you're talking about time, okay, how long is this video going to be? Is it going to be exactly 13 or 14 minutes? Or could it be 13 minutes and 45 seconds? 13 minutes, 32 seconds. So to deal with those situations, we have to deal with things a little bit differently. Okay? So, how we're going to do this is by using a density curve. You guys have seen these density curves before. This should be a review from chapter 2, I do believe. Okay? Yeah. Trash. Yeah. Yeah. And remember, the area under a density curve has to add to 1, just like all your probabilities in a probability table have to add to 1. Okay? For example, if we are looking, we're going to randomly generate a number between 0 and 9. Okay? So there's equal probability that we choose any of those numbers. And when I say between 0 and 9, I don't mean like 1, 2, I mean like 1.2, 1.21, 3.5. Okay? So, there's a 1/9 probability that, well, we have to make it 1/9 because 1/9 times 9 is 1. We need it so the area is 1. So we are finding, if we are finding between 3 and 7, we just do, well, what's 3 minus 7? Or 7 minus, whoa, that's too big. That's too, alright guys, we can do this. That's 4, right? So if you were to do this one, you do 4 is your width times your height, which is 1/9. So it'd be 4/9. Yeah, math. Let's do another example. Yeah. Alright, I want you to pause this and read it. Okay, guys? Because I'm not going to sit here and read it out loud to you. So, when I draw this graph, over here is going to be my probability, right? And down here is going to be time she walked. Now, where am I going to start this at? I'm going to start this at, what, 2. I'm going to end it at 5. Why is that? Because it uniform density interval from 2 to 5 minutes. So what should my height be? Well, from 2 to 5, I'm just going to add, this is not going to go well. Alright, cool, nailed it. Perfect. Alright. Why is it from 2 to 5? Because 2 to 5 minutes. So 5 minus 2 is 3. So the width of this rectangle is 3. So the height I need to choose in order to make it so when they multiply they equal 1 is going to be 1/3. Because 1/3 times 3 is 1. So it takes her 4 minutes on the bus it takes her 4 minutes. Oh, I'm sorry. On the bus it takes her from 2 to 5 minutes. It takes her 4 minutes to walk. So we want to know what's the probability that her walking will take more time. So we know walking is going to be 4 minutes, correct? And the train takes 2 to 5 with equal probability of each. So if we find the area of the shaded region, this means that that train took less time than her walking. So from 2 to 4, my width of that is 2. And I do 2 times my probability of a third, tells me 2/3, or 66%, right? Let's see if they agree with us. Hiya! Hey, that looks like a mine, but better. So we did the shade area. Yep, Probability that y was less than 4 is 0.667. So there's a 66.7% chance that it will be quicker for Selena to take the train than to walk on a randomly selected day. Awesome. We did it, team. Let's talk about one more. Now, not everything's uniform, right? Most things in the world that are continuous random variables are, not most, but some are normally distributed, right? Right here, when you look down here, you should see that and think of a normal distribution with a mean and a standard deviation, right? So let's say that we can model heights of women with mean of 64 inches, which should be 5'2", 5'4", good math, Mr. Terwilliger. Standard deviation is 2.7 inches. Now, if we chose a woman at random, we want to find the probability her height is between 68 and 70 inches, and we want to interpret the value. So when we look at the normal curve over yonder, this shaded area is what we're looking for, from 68 to 70, right? So there's two ways you can do this. This is a review too. You could find the z-scores and use table A. I'm not a big proponent of this. What I would suggest you do is, right now some bells should be ringing in your head. You take out your handy dandy calculator and use normal CDF. Remember, normal CDF, you're going to do your lower bound, your upper bound, your mean, and your standard deviation. Now, I wouldn't have done it the way that they did it. I would have done it the Mr. Terwilliger possibly cheating way. I would have done my normal CDF. I would have plugged in 68, 70. My mean was 64. And my standard deviation looks like it was about 2.7, right? And I would have gotten the same answer. You can do it either way. You can find the z-scores, use table. You can find z-scores and use normal CDF. Or you can do normal CDF and use the actual data. I got to check for time, y'all. They actually did the same thing. If I would have kept clicking, and they got 0.0561, and to interpret, hit the buttons. We can do it. The probability that a randomly selected young woman has a height between 68 and 70 inches is 0.056. Don't forget the randomly selected, and have a great day.